Hey kids, today we're going to talk about statistical analysis, and I want you to use 213's guided notes while you watch this video, because this will help you kind of follow along with what I'm about to say, and it'll tell you exactly how to skip around things and use my stuff when you are doing statistical analyses, specifically the t-test. So first off, at the very top, the purpose of a statistical analysis is to determine whether the results are found to be meaningful in an experiment. Just because we have two means and one is different than the other doesn't mean that that's the whole story, unfortunately. And you know that from all of the statistical anomalies that you had in 212. Whether it was a misrepresentation of data or the sample size not being big enough, so on and so forth. Additionally, a statistical analysis will actually answer our question if the experimental data supports a research hypothesis, meaning that it'll tell us exactly how likely it is we can accept that the research has an impact rather than that the research has no impact. We'll talk about what that means in a moment here. So in this video, we have an example study that we'll use to be able to go through this entire process of statistical analysis using two sample t-test. And this particular sample is going to be done by a researcher performing a clinical trial. Clinical trials are really good for this two sample t-test because we are comparing people who get the medication and people who do not. In this particular one, we're looking at a cholesterol medication in patients with hypercholesterolemia. The study hypothesis would be that the experimental medication that they developed would be more effective in lowering LDL cholesterol levels than the placebo effect, essentially, a sugar pill. So upon conducting the experiment, an investigator could find that the mean cholesterol levels of the group with the experimental drug is lower than the group that received the placebo, which would indicate that, hey, this drug is working just fine. This is what it's supposed to do. But that really isn't enough to be able to tell the whole story. This isn't enough information to conclude that the drug is more effective than placebo. We know that there could be too small of a sample size. We know that the results might not be statistically significant, so on and so forth. We have to put this in the context, and we have to put it into specific context of does it reject the null hypothesis that this doesn't work. So there are several types of statistical tests to analyze data. For this study in particular, for our study in this unit, we're going to use the two-sample t-test. A two-sample t-test is only used to determine whether there are differences between the means of two different populations. We could use this for men versus women. We could use this for old versus young. If you set an age for a change in the groups, like under 40, over 40, you could do postmenopausal, premenopausal, or postpubescent and prepubescent. In this case, we're going to use the drug and the not drug. So the first step in this whole process is to identify the null and alternative hypotheses. And this is kind of a strange thing to think about because we really do always have two hypotheses in our experiment. We have the null hypothesis and the alternative hypothesis. Both of these hypotheses should be set up before beginning the experiment, but in this case, we know that the researchers went through the process. We're going to isolate their hypothesis for them as if they hadn't done the experiment yet. Now, a null hypothesis, as we label as H0, is going to be the starting point in research where the investigator assumes there is no effect of the treatment. Literally, this person that's doing the research on the medication will assume that there is no benefit to taking this medication over the placebo effect. We'll typically set this up into an equality. So just like this right here, you see this mu symbol right here. Mu stands for mean. So the mean of group 1 will be equal to the mean of group 2. And that's exactly what that example says. This will always be the case for a null hypothesis. Null literally meaning none. So there is no difference between the two. That's why they're equal. However, what we really want to know is the alternative hypothesis, which we label as HA. We know that the research that we're doing is trying to figure out whether or not the drug works. So we're going to assume that the investigator believes this to be true and is trying to figure that out. So these means will typically be set up as an inequality, meaning that they're not equal. And there's two ways we can set this up. We can set it up directionally or non-directionally. Kind of makes sense when you hear them out loud here. A directional alternative hypothesis, one that is directional in nature, will predict that one mean will be bigger or smaller than another mean. So in this case, if the mean of one group, group 1, is greater than the mean of another group, then we can use the greater than symbol. Or if it's less than, we can use the less than symbol. There is another type of alternative hypothesis. We can assume that they just aren't equal, as in we can reject a null hypothesis if they aren't the same value. And so a non-directional alternative hypothesis is that the mean of one group is not going to be the same as the other group. It is just not equal to. So let's do a little bit of practice using our LDL study here. I want you to recall that there are two groups, and in this study, they're going to have 4 patients in each group, 8 patients total. It's not a lot. It's actually a pretty crappy study when you think about it, but we'll continue on so that we don't have to do too much mathematics here. Group 1 is going to be the group that receives the experimental drug, and so their mean can be listed as mu d, as in the mean of the drug group. Group 2 is going to be the group that receives the placebo, meaning that their mean is going to be represented by mu p, p for placebo. And what I want you to do is I want you to take some practice to writing a null hypothesis and alternative hypothesis here. Pause the video, see if you can come up with this on your paper there. This should be the back side of the first page, right where it says practice writing hypotheses. All right, take a second, pause the video. So hopefully this is what you came up with. The null hypothesis here is going to be HO or H0. And I wrote it as mu D equals mu P, as in the mean of the drug group should be equal to the mean of the placebo group. This is not to say that we are assuming that this will happen, but our purpose of this experimental design is to reject this. So we do have to note it to make sure that we are able to overcome this null hypothesis. Now, the alternative hypothesis is what they really want to know. They really want to know whether or not this mean of the drug group for LDL is going to be less than the mean of the group for placebo effect. So really we're looking for a less than effect here because we want the LDL groups to, or numbers to be lower. So we're moving right along, and we're going to talk about setting a level of significance. What this really means is, what is the threshold for us to say that this statistical study is significant and is valid? What is the threshold of me finding out that, okay, my two means are different, or one mean is indeed lower than the other, and I can prove it in my stats here? So what we need to do is we need to set the level of significance, which we call alpha, before the investigation begins. We need to figure out exactly how many times I'm okay with the same event happening by chance. So alpha is used to determine the percentage of results that occur only due to chance, as in flipping a coin over and over again is 50% heads, 50% tails. I really don't want my statistical design to reflect 50-50. I'd rather have, oh, I don't know, 90% of the time that my particular event, my experimental design, occurs again and again and again, that these results will be the same. Really more likely, I would love to have a reliability of 95%. So when our alpha value is going to be 0.05, that is that 5% of the time that this event will occur only by chance and won't be repeatable, 95% of the time it will be reliable results. And these are pretty typical values here. We have an alpha value of 0.01. That's a really, really good score because that would indicate that this same setup would happen 99% of the time, and 1% it might be different by chance. This again would be 95% to 5%. This would be 90 to 10%. We can also use this value to determine whether or not our null hypothesis should be rejected, meaning that if I can assume that my results are reliable and have this alpha number be as low as possible based on my statistics, I can actually reject the null hypothesis and accept the alternative hypothesis in the meantime. So for the LDL example, we're going to assume that the alpha is going to be 0.05, meaning that 5% of the time these scores will just occur by chance. 95% chance that the results will be similar if this investigation is repeated many times. And that's the whole idea between experimental design, is we want this to happen over and over and over again. So 95% of the time it happening again is a pretty good score. So now the investigator now will conduct the study and set up the data to be analyzed with this 95% in mind. So once we have the data, it's time to calculate the mean, the variance, and the standard deviation of our data set. And we have done things like this in the past. We might not have done the mean, standard deviation, and variance together, but we have done something like this in other science classes. So here's the experimental data that I have for our LDL, and this is following along with the third page right above the Roman numeral 3 here. If we consider that 8 patients were treated, 4 of them having the experimental drug and 4 of them having the placebo, here are their LDL levels after their medication, whether it was placebo or not. One patient had 159 as their milligrams per deciliter, one had 169, one had 133, 126, and on the placebo side, 174, 151, 148, 156. Looking at this with blind eyes, we can see that this mean is indeed going to be lower than this one, but we need to be able to calculate such a thing. So here is the formula, the arithmetic formula of the mean, which is going to be this x with a line over it. X being mean, line being average. The arithmetic average of this is going to be the sum of all x values, the values that we have in our data set, divided by the sample size, which is labeled as n. So if we're going to do the calculation on the LDL levels, I have the placebo over here on the right side. You can see that my 4 pieces of data are right here, 174, 151, 148, and 156. Adding those together and dividing by 4, making sure that you use order of operations by using this as a fraction and adding the stuff first, hitting the equal sign, and then putting in the divide by 4, you should get a mean of 157.25. Go ahead and pause the video and try to get your other 4 patients from the experimental medication calculated over here on this side. Reminder, this data is above the Roman numeral 3 in your packet. I sincerely hope that this was easy for you. The mean for the experimental medication should be 146.75. Adding those up, dividing by 4, you get the idea, hopefully. Now, on the next page, it's going to talk about variance. And variance is just a measure of the spread of the data about the mean, meaning how much does this data stray away from the mean, and how often do these data pieces actually occur outside of the mean. The more spread out the data points are, the larger the variance is going to be. And this variance is labeled as S squared. S, as we'll find out in a second, stands for standard deviation. So really we're finding the variance first, and then we'll use this value to find the standard deviation. This is a tricky order of operations, so you have to pay attention to it as you go. Here is the equation. Variance equals the sum of the data point minus the mean. Square that before you add the sum, and then divide by n minus 1. Here it is step by step. We're going to first calculate the difference of the data point from the mean for each and every data point. So that means we take one person's data point and subtract away the mean. We then put another one and subtract away the mean. Put another one and subtract away the mean. And then we're going to square each of those deviations, meaning every single number we just calculated, square them. Then you will add those numbers all together giving you one big number on top. And finally, we're going to divide by the number of data points in the data set minus 1. So in this case, the data set has 4 entries, and minus 1 is 3. We divide by 3. So you can see this on the right side here for the placebo. Here are the values that we have again. The average that we had was 157.25. I should say the mean was 157.25, not the average. Looks like I need to take that number away from each of the values that we have. That gives me a difference of 16.75, negative 6.25, negative 9.25, and negative 1.25. And then I square each of those numbers. If you end up getting a negative number after this step, you've done something wrong. If you square a negative, you should get positive every single time, I promise. Okay? So after squaring 16.75 to 280.56 and yada yada so on, you then calculate the sum by adding those squared numbers together. So it's going to end up being a pretty big number compared to the mean on top, and that's okay. Instead, we're going to divide by the number of data points minus 1. So that's 4 minus 1 is 3. 406.77 was the sum of all those numbers. Divide by 3 gives us 135.59. I invite you to pause the video and try to do this for the 4 patients that you have before treatment. You'll be asked to do this in some kind of statistics class. I will not be able to give you the answer because I don't have it written down and I left my scientific calculator at school, so I can't do order of operations with my dinky little phone. Sorry. If you'd like to check your answer with me after watching this video, please do so. I'm happy to give you answers as we go and check your work. Remember, I used to be a physics teacher. I know math. Okay? So remember, we just talked about variance, which is the measure of how far away the data is from the mean. The standard deviation is very similar. It's going to be a measure of the spread around the data, not just how far each individual data point is, but how much does the entire body of our data swell away from the mean. And this is going to be a square root of the variance, meaning that all we need to do is the same stuff we just did, calculate the variance of the data set, and then just take the square root of that number, and that should give us S, our standard deviation. That's why that last one was S squared, because variance is just the square of standard deviation. Now we just take the square root to solve that problem. So you can see on the right side that they calculated the variance again of this LDL. We got that 135.59 last time. We just go ahead and take the square root of that variance, and our standard deviation is 11.64. A good way to think about the standard deviation is if we were to repeat this experiment over and over and over again, we should expect that the numbers that we get should be about 11.64 above the mean or 11.64 below the mean for at least 2/3 of our data set. It won't be exact, of course, but that is kind of what we should expect from our standard deviation. It should be 2/3 of the numbers within the range plus or minus 11.64. Again, I invite you to take the variance that you just calculated last time and take the square root of it to find your LDL of your treatment group. I will not be doing that. I will check your work though, so let me know. And here we are with all of our numbers that I did not have for you, so now I do have them for you. What do these results really show? And this is at the bottom of the page right after the standard deviation. The mean of the LDL values for the subjects given the experimental indication on the left side in the center column were indeed lower than the subjects given on the placebo, but notice that the standard deviation was a lot higher, which means that the range of individuals in our group had a lot more variance in it. In fact, you can even see the variance itself, how far away these numbers strayed away from the mean, is very, very large. Now the researcher will go ahead and determine if the observed difference is statistically significant or if it's just a bunch of gobbledygook, okay? And we'll do this by going ahead and using this two sample t-test like we've been talking about, making sure that this is not by chance. And so we are finally on the fourth step. Our fourth step is to choose an appropriate t-test. And this is going to be extremely important, especially for your experimental designs, because you will also have to choose an appropriate t-test based on your statistics and your data sets that you get from your test subjects. Now, there are two main types of two sample t-tests. This is starting at Roman numeral 4 in your packet here. We have an independent t-test, where the two groups are independent of one another. Makes sense. And we have a dependent t-test, also known as a paired t-test, which means that the two groups are kind of dependent on one another, much like a before and after. This would be good for a medication if we wanted to see before the medication was taken and after the medication was taken. And each type has several variations that depend on experimental conditions, so this is where you want to pay attention for what kind of t-test you should use when you're coming up with your human physiology projects. So an independent t-test is going to be used to determine whether the difference between the two means of two independent populations, two separate groups that are being tested for the same dependent variable, men and women, for example, being tested for heart rate, is statistically significant. That's the same dependent variable, the same outcome that we want to see in the same data sets, just two different groups. The example that they have here is a study where one group is given an experimental device and the other group is given a placebo. We can test the group that has the experimental device and the group that doesn't have the experimental device and see the difference in the means and see if it's by chance. Now, the formula used will depend on, specifically for variation, the formula used will depend on the number of samples taken and if the two groups are equal in size. There are three different versions of this, and like I said, this is a lot of stuff altogether, so you might not even have to use any of this stuff, especially given that we're going to have such varied different amounts of data sets. So you want to ask yourselves these questions over here before selecting a formula if you are to calculate this stuff. Are my sample sizes unequal? That's the first question we should ask ourselves. If they are, then you could have either this massive formula over here or this one down low. If your two sample sizes are equal, then that actually makes life a little bit easier. We only have one equation for that situation. The other question we have to ask ourselves is whether or not our sample sizes are small. N of less than 30 is typically small enough to say that this is a very small study. That's 30 total, by the way, not per group. So the N minus or less than 30 would probably have to use something like this to try to get the variance to be a little bit more exact. This one, we have to do a little bit less to be able to get the independent groups. And this would be both sample sizes being larger than 30, so the N in both sample groups being 30. We want the N to be less than 30 for this one here. Now, a dependent t-test is going to be used to determine whether or not the difference between the means of two groups with the same participants are being tested at two different points is statistically significant. As in, if I were to have a group of participants tested before an experimental treatment and then after experimental treatment, we would use a dependent t-test to see the differences between each of those individuals before and after. We can literally see how one improves and how one not improves. This would be really good for something like a reaction time test where you have a patient test their reaction time or their short-term memory and then do something to them and then test it again to see how that does something, changes their memory or their concentration. And there is only one formula for a dependent t-test for the variation. We will use specifically this right here. And this is actually the t-test formula. So we'll be using this with the paired samples to be able to get the difference between each of these data sets from before and after. Again, you might not need to use this. You might be able to use my calculator online to be able to enter your statistics in and have it do it for you. But we better know how to read those numbers. So back to the LDL treatment medication experiment, we need to determine what kind of t-test we should use, which one's more appropriate. If you asked yourself, hey, are we doing a before and after, or are we doing two different groups? Well, we're doing two different groups. So the best answer for us right away is going to be the independent t-test because we're testing an experimental group and a control group. Then we have to ask ourselves which variation of the formula for the t-test should we use. And both groups have 4 participants, so even though it is a low sample size, the first stipulation is that we have equal sample sizes in each group. So that is satisfied right here for our second equation, and we get to use the short one here. That's so nice. So after we select the proper t-test, then we actually have to calculate this t-statistics and find the degrees of freedom within our test result to be able to determine whether or not we can reject or fail to reject the null hypothesis. So here is that formula that we just chose for our investigation on LDL. I believe this formula is listed again right before the Roman numeral 5. You will not have to use this equation. I will be giving a spreadsheet that will do the calculation for you. But if you love math and you want to check your work, knock yourself out. I will be there to help you out, I promise. I will do the math with you. Now, this t-statistic value is going to be just a number. It is going to be a value. But this value is going to be extremely important because we're going to be able to determine whether or not the null hypothesis should be rejected or can't be rejected, as in whether or not our statistics are valid or not. So here is their math doing the t-statistic for the experimental drug group, specifically to compare to the placebo here. So what they did was they took the experimental drug group's mean, and that would be x1, and the placebo's mean, that would be x2, and put it in the top of the fraction there. You end up taking the absolute value of the difference between those two, which means that this will always be a positive number, and that positive number is 10.5. Not super tricky math right there. In the bottom, we're going to take the variance of the first group, that would be 421.58, and add it to the variance of the second group, 135.99. You can see that right there. And multiply that sum by 1 over n being 4 because that is the number of individuals in one group. So 1 divided by 4 times all this stuff becomes 1 divided by 4 times 556.97. Divide that by 4, we got our 139.24. Make sure we end up square rooting it because we want to get the standard deviation instead. That would be 10.5 divided by the square root of 139.24. That's going to be 0.89. This number doesn't mean a lot to you right now, but it will in just a second, I promise. Now we know the t-statistic, we should get the degrees of freedom. And this is a much simpler calculation, I promise you. V, the degrees of freedom value, is a measure of certainty that the sample populations are representative of the population being studied, meaning that we took a sample of 4 people from each group. Does this represent the entire group of everyone who would ever take this medication or everyone that would ever take the placebo? Well, in order to be able to determine that, there's a value that we will use called degrees of freedom to be able to compare our t-statistic to. And obviously, the more people we have in our study, the better the degrees of freedom value will be, and therefore the better our statistics will be. So keep that in mind when we do our experimental design for our tests next week. You'll want to actually get as many people as possible to make your statistics as valid as possible, to get this degrees of freedom value as low as possible. So, how do we calculate the degrees of freedom? Well, first we have to figure out which of the t-tests we just used. We still are using the independent t-test and that formula number 2. So we're going to take the number of individuals in group 1, that was 4, and add it to the number of individuals in group 2, that was also 4, so 4 plus 4. And we're going to subtract away 2, meaning 1 per group, as in one of each of the groups could be done completely at random or could be at fault for chance. Okay, that is our degrees of freedom calculation. This you will have to do on your own. Sorry. So, like I said, if we plug in 4 for our group 1 and 4 for our group 2 and subtract away 2, our degrees of freedom value is going to be 6. And we're going to use this value to be able to determine how valid our t-test value is for this small of a group. We've just calculated all this. We're not just done yet. We're going to use a table. This is an epic, like everyone in the world uses the same values for the t-test table to reject or fail to reject our null hypothesis. If our value is greater than the value we need, as in if our t-test is greater than the value that our degrees of freedom allows in this table that we're about to see, then we can reject the null hypothesis and say that our stuff is true, that our means are statistically significant. And that's exactly what we're going to do. So for the last step, we're going to reject or fail to reject the null hypothesis. Here's a reminder of what our null hypothesis was. Our null hypothesis was that the LDL levels for both groups will be equal. We know they're not exactly equal, but we're talking about statistic equality, meaning whether or not they are equal-ish, equal enough that we can't really reject the null hypothesis, and therefore it's not a big enough difference that this drug should be on the market. So the critical value will be compared to the t-statistic. This critical value is the value that we have to overcome with our t-statistic based on the degrees of freedom that we have. And you're going to be looking at the t-statistic value in the very last page of your packet here. This is a small version. I have other bigger versions if we need to do so. And this will be compared to the degrees of freedom that we just had. Here is the value on the computer. We can see that on the left side, we have the degrees of freedom listed. This is what we're going to start with in our abbreviation of the t-test. And we're also going to look specifically at the alpha values. Remember, the alpha is the value that we will compare for how likely we are to chance. And we want our alpha value to be 0.05, which means that only 5% of the time will this experiment reoccur randomly by chance. We want this to reoccur on our own terms 95% of the time and be true every single one of those times 95% of the time. So if we're looking at our values here, we can actually determine that 6, our degree of freedom, and 0.05 intertwine right here at 1.943. And I think that's what my next slide is going to say here. Yeah, we just use the column on the left for the alpha value and the column on the row corresponding to the degrees of freedom, just like we did with my mouse just now. The LDL treatment, blah, 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 we did that. The critical value that we found is 1.943. What does this critical value mean? Well, our t-statistic value was 0.89, which means that our value did not get bigger than the critical value of a t-chart, meaning that our critical value says that in order for us to accept our test as valid and not by chance, we need our t-statistic to be higher than that critical value. And the only way to do that is if the variance is smaller, because that's what the t-statistic is calculated based on. So, because our t-statistic value, 0.89, is lower than our critical value of 1.943, then that means that we fail to reject the null hypothesis, and the results of our test are not statistically significant. Meaning in this particular case, there is no difference between the LDL levels of the two groups. The placebo group and the group that got the drug had basically, statistically, the same levels of LDLs by the time they were done with the, uh, the treatment. And this observed difference was basically due to chance. We got lucky that the medication worked in the way that it did. So based on the t-test, and the investigator can conclude that the results were not statistically significant. This means that the new medication did not lower the patient's LDL more than the placebo. In summary, we're going to be using these two sample t-tests to determine whether or not two groups and their means are really actually very different. You might want your values to be the same across, and that's totally fine too. Your null hypothesis would be different in that case. But more often than not, you want to see a change between two groups, whether it's before or after, or men versus women, old versus young, so on and so forth. And this t-test is actually going to see if these two means are real and actually different. We call that significant, a real difference and not due to chance. If we can't reject the null hypothesis, then our results can be determined to be not significant. In fact, I believe 2 of our 4 physiological experiments last year with last year's seniors were not statistically significant. So don't worry, we might have some non-statistical significance. That is the video. I went fast. Hopefully you paused. If you did any of the math and you want me to double check anything, please let me know. If you still have questions, please let me know. I'm happy to go through, especially this critical value chart right here that we did right here. I'm so good at reading this, and there's so many other versions of this critical value chart that have higher degrees of freedom that we'll probably use from time to time for our data analysis for our experiment. Please ask me for help. This is something I'm really good at, okay? One more thing before I let you go. So I told you that I would be giving you a basic statistics calculator specifically for our class. And this is a t-test calculator that will do all the work for you. I'm going to use the values from our LDL and placebo data set that we just had, and I'm going to put them into this spreadsheet for us here. So let's zoom in a little bit just to make it easy on us. Patient 1 had an LDL of 159. Patient 2, 169. This is group 1, so 133 and 126. I can even come up and say that this is my medication group. Okay, and notice that the chart automatically updates based on this. Now, when you're doing this with your own data set, please be sure that you're using the appropriate t-test, whether it's the independent t-test or the dependent t-test here. Group 2 for our example here was the placebo effect here. So I'll have the placebo group here, and that's 174, 151, 148, and 156. Based on this chart right here, it does look like the means were different. However, we actually have the t-test calculated for us down low here. You can see all the statistics that mean something to us. The count is 4 for each, the minimum, the maximum, the mean calculated for us, the median, not necessarily always super useful. The variance is calculated, the standard deviation is calculated, standard error is calculated, basically how wide a margin are we allowed to accept for our due to chance for each group here. And the confidence interval is just basically the standard deviation compared to the 95% that we really want us to see. Here's the meat and potatoes of it right here. The t-test was 0.899. That was the same number that we got from all that arithmetic that just went on the slide before us. And the degrees of freedom was something that we calculated right there. That was easy to do. The calculator does it for you just based on the numbers from the count. So we go over here to the example critical value chart here, and it does have the information for you on what to determine as a significant value here. But again, we can just go to 6 and the alpha of 5%. So that's a 95% interval. That would be 1.943 right there. And that is much higher than our t-test right there. I want to show you one more thing here. This p-value is typically associated with the likelihood in which the values are recurring for chance, meaning that if we reject our null hypothesis, then we still kind of want to know how often we could assume that these patients will have these values. And this one shows us that zero point 0.4 means that 40% of our time, our patients will have values that fit either one of these categories here. So it doesn't really matter whether we have the medication or the placebo, because 40% of the time, those patients are going to have the values that are close together anyways, which means that we can't really assume that these means are any different. 40% of the time, they're not going to be different, and that's not good enough. We want this value to be as low as possible. Again, this is a critical value, so we want this to be as low as 0.05. This is a little different than the actual alpha. This is more like a correlation statistic. And when we get to your independent projects, if you're doing something with correlation, I'd be happy to talk about that more for sure. And I'll give you a different calculator for that. Okay. That is it for me. You can see that on the other slide here, we can do a dependent t-test for before and after instead, which is awesome. Okay. That's it. I'm done talking. I can't talk anymore. Please ask for help. I'm happy to help out along the way.